In this video, we consider two languages, A and B, that are both subsets of sigma star, such that A intersect B is the empty set. So A and B are disjoint, there's nothing in their intersection. We define a language C, which is a subset of sigma star, as separating A and B if A is a subset of C and B is a subset of C bar. So here we mean C complement. Prove that if A and B are co-Turing recognizable, which means that their complements are Turing recognizable, then there exists a decidable language C that separates A and B. When given a question of this type, the best thing to do to start off, if you're not sure, is to write down what you know and what is implied by what you know. So let's write down what we know. We have a picture. This is our universe. This is sigma star. This is language A. This is language B. They are disjoint, so there's nothing in their intersection. Okay, we know that A complement and B complement are Turing recognizable. And that is all that we know from what we're given. Okay, now what we want to prove, so we'll add it to our picture. I'm going to use dashed lines to show that this is what we need to prove. We need to prove the existence of a language C such that A is a subset of C and B is a subset of C bar and C is decidable. So we need to prove that there exists a C such that A is a subset of C, B is a subset of, sometimes this notation helps, sigma star minus C, which is C bar, and C is decidable. Okay, this is what we're working from. Now what can we imply from what we know? Since A bar and C bar are Turing recognizables, are Turing recognizable languages, then we know there exist recognizers, so Turing machines, J and K, such that let's let the language of J be A bar. This means J recognizes the language A bar, and let's let the language of K be B bar. So K recognizes the language B bar. Okay, so that's something that we know. What do we know about running J and K in parallel? Will we eventually get every string in sigma star? If we notice that from our picture, A bar, what is A bar union B bar? Let's make two pictures here. So we have A and we have B. Then A bar is everything out here. So this is A bar. I can't write down there. A bar. And B bar is everything over here. Okay, so if we think about our sigma star, our universe, everything in the universe, every string is located either in A bar or B bar, which is exactly the union. Okay, so we know that the union of these two covers every string in sigma star, which also means that either recognizer J or recognizer K is going to recognize every string in the language. If we pull everything that J recognizes and everything that K recognizes, we're going to get sigma star. Okay, so if we run J and K in parallel, we will eventually accept every string. Okay, so running J and K in parallel will eventually accept every W in sigma star. Okay, so why do I say in parallel? Remember, these are recognizers, so they could loop forever on some string. So I clearly don't want to try running, say, wi first on j and then on k. If I'm a Turing machine and that's part of my procedure, then it's very possible that I will run forever. Okay, and what we actually want to do is eventually accept every w. And if I run forever on wi, I'm never going to get to wi plus 1. Right? I'm never going to get to try the next string. So even if the next string was in sigma star, I won't ever get there, so I can't ever accept it, and therefore I don't actually accept sigma star. Okay, so that's the logic whenever we say running something in parallel. It's usually because we have recognizers and we need to be careful about this case. Okay, so yes, okay. So now what we want to do is we want to try to construct a decider for this language C. Now note, I'm not saying I know what C is. We just need to prove that it exists. We don't need to prove that it has a certain number of strings in it or that it has any property other than it's decidable. We just have to prove that it exists and it's decidable and that it has this one condition that A is a subset of C and B is a subset of C bar. So that's what we're going to try to do, is build a decider for a language C that has those two properties. Okay, so let's call it T. And what is T going to do? On input W, we are going to do exactly what we were talking about before. We're going to simulate J and K in parallel on W. Okay, so we let J take one step on W, and then K takes one step on W, and then J takes 2 steps, and K takes 2 steps, on and on and on. Okay? If J accepts first, we're going to reject. If K accepts first, we're going to accept. Okay, notice that one or the other is eventually going to happen. This is what we were talking about on the last screen. So either J is going to accept, or K is going to accept, or they're both going to accept. Okay, so we'll prove that in a minute. But because we have either one or the other or both eventually accepting, we will either reject on W or we will accept on W. Okay, so this is in fact a decider. Okay, so what have we've proved? We've proved T is a decider. Okay, let's talk about each of these cases. So if J accepts, what does that mean? Remember that J was the recognizer for A bar, so that means W is an A bar. Okay, go back to our picture. What does it mean to be an A bar? This one's B bar. The other one's A bar. If it's an A bar, it means it's not an A, and it might be in B. Okay, so here I really mean if J accepts first. Let me add that in. If J accepts first, W is in A bar, so W could be in B. We don't know. It might be in neither, right? It could be in neither A nor B. That would still be an A bar. But W could be in B. Okay, so if W is an element of B, it can't be in C. Why? Because B is a subset of C bar. So if W is in B, it definitely can't be in C. Okay, and then what do? We reject. Okay, so we've decided this string can't be in C. If K accepts first, what does that mean? Remember, K is the recognizer for B bar. It means that W is in B bar. Okay, so W could be in A. Again, not necessarily, but it's definitely not in B. And that's all that matters here. Okay, so as long as it's not in B, it's okay to put in C. So it could be in A, but not B. So W is okay to put in C. Okay, notice that what we're actually doing is kind of constructing C. I said I don't know what it is, but we're going to show that it exists. And if we construct it in this fashion, we're showing that it exists. Okay, so this is what happens if K accepts first. It's okay to put in C, so we go ahead and accept. Okay, notice that's what this Turing machine does. What is the third case? Okay, so the third case is that both J and K will eventually accept. Okay, notice here one of them is going to accept first. All right, but it could be the case that both of them would eventually accept. Okay, so what does that mean? It means W is not an element of A, but also that W is not an element of B. Okay, so it's okay to put W in C. All right, C is a superset of A. We don't have to make sure everything in A is in C. The restriction is that nothing in B can be in C. Okay, so here I'm actually showing that even if both J and K would eventually accept, it would still be okay to put that W in C. So it really doesn't matter which one accepts first if both J and K accept. Okay, yes, okay. All right, and we also note it can't be the case that both J and K reject. Okay, why? Recall language of J is A bar, language of K is B bar. So if both J and K reject, it means that, so if both J and K reject, then W is an element of not A bar or B bar. Okay, they both reject, so it's not in the language A bar and it's not in the language B bar. Okay, and then by De Morgan's law, we're going to get A double bar intersect B double bar. And remember that double bar is just the same thing as no bars. So A intersect B. What is that? That's the empty set. Okay, a string can't be in the empty set. Even if it's epsilon, it can't be in the empty set. That's what the empty set means. Okay, so if both J and K would reject, notice they're recognizers. They may not have to reject, but they could both say fail to accept. Okay? Or fail to accept. This works for both of those. Then the string is in the empty set. Happen, so we get a contradiction. Okay, so what does this mean? It means that we are going to hit either the first case or the second case. Okay, and this third case was just saying if they would both eventually accept, it's okay. It doesn't matter whether we put the string in C or we don't, based on the answer that we get from the recognizer for A bar or the recognizer for B bar. Either way, it's okay, so we just go with whichever one accepts first. So if A bar accepts first, then we don't put it in C, and if B bar, the recognizer for B bar accepts first, then we do put it in C. Either way, it's fine. Okay, so we've showed that we're going to hit one of these two cases on every single string. That's what this bottom case told us, that this case can't happen. So we are definitely a decider, so we've proved T is a decider. Okay, and if we look at the properties that we have, that we've been explaining throughout, we actually have also met this property. We've met the property that as we're building C, if we decide first that the string is in A bar, we're going to reject. We're not going to put it in C. But if we decide that the string is in B bar, we're going to go ahead and put it in C. Okay, so this means, so we've also satisfied that B is a subset of C bar. Okay, that's what this means. And A is a subset of C. Okay, this one is a little hairy to see. Okay, but you should be able to see it from the proof. Okay, so therefore C is decidable and C separates A and B.